Good afternoon. Welcome to EMC Live MIL-STD. I'm James Rango, editor of Interference Technology magazine. If you were here for our opening keynote this morning, you already know our next speaker. If not, let me introduce Stephen Ferguson, Principal Consultant at Compliance Direction LLC. He spoke with us earlier about EMC testing preparedness. In his presentation, he'll be focused on a specific set of requirements, MIL-STD-461G. Steve will review the changes in the G revision. You can submit questions by using the Q&A panel on your screen. Steve will address as many as he can at the end of this session. Steve, welcome back, and the floor is yours.
Well, good afternoon. I appreciate the kind introduction. And today's topic, as you heard, is MIL-STD-461G and associated calibration verifications. So why do we do this verification process? Well, we need to provide assurance that the system works good. It checks the hardware as well as the software. We create signals and determine that we measure them properly. We create the fixed value. And if everything is connected right, all of the various components in a typical configuration, we should get the right answer. And our software brings in correction and conversion factors and things of that nature. And the hardware has all kinds of connections made with potential for attenuators, filters, etc. And all these components get validated by having a known signal that we measure. There's also a second part to that to establish some test level control limits. Sometimes in susceptibility testing, there is a requirement to set a maximum drive level, and we configure it according to the standard and use that as our top level susceptibility waveform. So we're going to discuss a few of those things. This is accomplished in conjunction with the test. This is not done once a year or sometimes. This is a thing that says when I'm using the equipment that I have here for this particular configuration, I'm going to check it and its connections. And then when it comes time to move that into the test bed instead of the calibration verification, we minimize how many things we do that could alter the connections and disconnections and things like that that could end up with a defective junction. So that's what our theme is today. MIL-STD-461G, released in late 2015, implemented a change in the calibration process, stating that after the initial calibration, passive devices such as measurement antennas, current probes, and LISNs require no further formal calibration unless the device is repaired. So with that came about an exemption here, and so we needed to be able to see, does it need repair? The whole idea was that we can reduce a lot of these things that typically are not changing in the way they perform. So this change allows a lot of periodic calibration reduction and some cost savings passed on to the laboratory. We were doing verification checks, and some of these things, in order to be complete, the verification checks were simply expanded to bring in more frequencies, a few other tests to validate these passive equipment items during any one of the formal calibration things. So the idea was very good, but it's not without some additional cost that we do every time we do the test. But don't get me wrong, that this calibration check did a good thing, but we need to consider what effects it had too. When those changes were implemented, the revision G also put a few more checks in place. The verification process become up somewhat expanded with additional frequency checks and some additional tests that became necessary because we weren't doing the periodic calibration. So without having these additional things, we ended up with a bigger gap. Now, this is, as I mentioned, a thorough physical inspection remained. we needed to do that. It was critical because now the spot checks don't cover all the frequencies, and some items are not physically present in the verification configuration. So we need to consider some of the pitfalls that come about in dealing with this thing. That little chart that you see on the slide there showed a cable pinch at a very high frequency. I forgot the exact numbers here, but in the article down below, those were known. But a cable pinch or a connector spread where we've cross-threaded a connector or something like that to damage the pin, where the pin, especially the shield terminal, is not making good contact all the way around. So what happens is we see an impedance mismatch, and it can be limited to a very narrow frequency as shown on those charts. That chart shows a couple of frequencies that popped out. And by the way, there's a little dot on the end that showed the spot check frequency, which would not have found that cable flaw. And physically inspecting it, how do you make sure that the cable's not pinched somewhere along the line? If it's a very damaged cable, but it's easily visible, but it's not something you can see very easily unless it's really deformed. And this one was not physically visible until pinching the cable. We were seeing a slight depression at near one end of the connector, out of the cable. So shield terminations could become problematic. Loose fittings, corrosion gets into it, especially antenna elements that are screwed together. If they vibrate and come loose by some quirk, we might not necessarily find the issue here. And we also have some pitfalls in record keeping. We tend to check these things and get all the charts and graphs and things like that and put it into the report. But we don't put a log on the calibration of that device to show that we did check it occasionally. So record keeping can become a potential good thing. That article that I referred to there at that website, that link, I did that. That article is published through Interference Technology, but my website puts a link onto it. And it talks about some of the pitfalls and taking care of record keeping and things like that for a better discussion on some of the elements associated with what we're doing here. So without further ado, let's go into some of the various test methods and talk about the verification process, the calibration verification process, for a few of these on how we do it, what things we need to concern ourselves with, and things of that nature. CE 101, and I'm just putting them in some not particular order for our discussion here. It checks the probe, the cable, the receiver, and the data collection software. We could also have other components that would be in the measurement path between the current probe and the receiver for certain applications, and they would need to be present as part of this calibration check also. Basically, you would put something together here, and we look at what the voltage across the resistor needs to be to produce a current that is 6 dB below the limit. So we want to produce the current limit on 6 dB. 6 dB is one of those default things to see that we can measure and accurately measure below the applied limit line here. We adjust the signal generator, and we might have an amplifier involved depending on what resistor you chose, to attain the resistor voltage at the test frequency. Execute the measurement receiver program to collect the data, and have the software apply all the corrections and conversion factors, and confirm that the measurement is within the system. So the idea is here, what resistor value is chosen? Well, you don't want to put a large resistor in here because it would take too much voltage coming out of our generator and amplifier to produce a nominal current here. So we want to have some sort of limiting factor. I usually pick something in the 20-25 ohm category, 10, something like that. And then we place the oscilloscope across that to measure the voltage. So I asked the question down here, is the oscilloscope set for a high impedance or a 50 ohm termination? Well, you're going to typically use a high impedance. If I put a 25 ohm R in that case, and the oscilloscope is set for 50 ohms, my real impedance is somewhere down in the 30 region. So I'm not doing a calculation based on a 25 ohm resistor. Excuse me, 30 ohms. It's down way below the 25 ohms because 50 is in parallel with it. As you can see, I don't do the math in my head too much. But the idea is that putting an oscilloscope in 50 ohms in parallel with the R changes the value of the total R, and current will change. So no longer is that voltage valid. So the whole idea in picking and deciding for yourself whether the oscilloscope needs to be 50 ohms or not is determined by, we look at the circuit and say we do not want the measurement equipment changing the values of the measurement. We see this in routine situations. So the idea is using a high impedance will have a minimal effect on a 25 ohm resistor. So to do that, we would adjust the voltage to the right level and see that the current is measured. We calculate all those values. As you could tell by the last slide, I don't get into all the specific calculation and details. This forum doesn't provide near enough time to do that. So you need to look at it. If you need much more detail involved, attending a training course that covers the detail might be appropriate. Anyway, let's go on to CE102 verification. We have a test setup that's like we're showing there, and this is kind of following the MIL standard, where there is an attenuator present in the measurement line. Now that attenuator may or may not be necessary. Sometimes you need to have something there to protect your receiver, because when the power turns on, the Listen capacitor will tend to short circuit and put a high voltage into the circuit there. And so the capacitor will act like a short circuit initially, as we know that's how they act. So the attenuator protects the measurement receiver from an overvoltage surge at turn on. So, and after that, you may or may not need it because the Listen capacitor tends to attenuate the signal. Anyway, this checks the Listen, the cable, the attenuator, the receiver, the data collection software. And we configure it like we show there. And after the lower frequency checks, the ones at 10.5 kilohertz and 100 kilohertz, we get rid of that T in the oscilloscope, because we need to have something there, because when the Listen comes into being here at 10.5 kilohertz, the Listen impedance is approaching about 5 ohms or so, and the signal generator is looking for a 50 ohm termination. So what happens is when I attach it to 5 ohms, I load the signal generator output. It reduces significantly, so we need to adjust the level based on what the oscilloscope measures, not what the signal generator says it's outputting. So it compensates for the losses associated with the overloading by the Listen. We determine the voltage limit minus 6 dB, adjust the generator to the level, remember using the oscilloscope to set the amplitude at the lower frequencies. Execute the measurement software, apply the applicable corrections and conversions, and confirm the measurement is within the limit. And then we need to do a second step to this. And this comes about because the periodic calibration is not there to show that the Listen impedance is in fact correct. The Listen impedance, instead of showing a 5 ohm at 10.5 kilohertz, it may be something is wrong with it. It's showing 12 ohms. So the impedance would be off because of a value change within the Listen. So what we do is, while we're at these voltage levels of 10.5 kilohertz and have the voltage applied measured with the oscilloscope, we disconnect the listen. So we've taken that excessive load or overloading away, and this amplitude on the oscilloscope will elevate because the generator is not loaded. And that elevation factor tells us how much the impedance is by the calculation. At 10.5 kilohertz, we expect about 14 dB of change. It goes up by 14 dB. So the loaded and unloaded test is an additional step, because we're not doing periodic calibrations, to verify the listen impedance. So it's good. A question I've already kind of answered was, why is the attenuator present? Quite frankly, it shows up in there. Some people use a transient limiter in place of an attenuator because it still provides a protection and maybe not as much loss to the signals that we're measuring. Remember, if I put a 20 dB attenuator there, and I think the standard says 20 dB, then we've lowered our sensitivity by 20 dB, attenuating the signals. So depending on the limits, there should be enough measurement sensitivity room, but we may not need it for particular limits and etc. So the attenuator is there, it serves a purpose, but it may not need to be there all the time. CE106 verification that comes about is pretty straightforward. For the receive mode, we don't have a lot of circuits where we have requirements. We simply connect our measurement receiver directly to the antenna port of the UT, and all these other things probably are not necessary. A preamp possibly. But in the transmit mode, we're generating a high power signal coming from the EUT. So we need to put all of these things in here to attenuate the intentional transmission so we can measure with the dynamic range necessary. So we inject a signal at the end of the cable through the attenuator, through the directional coupler, over to the rejection network, and that could take on a low pass or a band reject or a high pass. Could be all three depending on frequencies we're looking at, into our attenuator and receiver. And the calibration checks all of those things. Now, for elements where there is a lot of power coming out of the EUT, some of these things may need to be big enough to where I don't have enough range in my signal generator to be able to overcome all the losses. I could put a 30 dB attenuator in here and a 40 dB directional coupler. I've lost 70 dB of signal. The rejection network may take away 30 or 40 dB more, so I'm down 110 dB, and I can't compensate for that much with a normal signal generator. I'd have to generate an almost intentional transmission to validate that. So what happens is we check maybe the attenuator independently of the directional coupler, the coupler independently of the rejection network, etc. And then we check the rejection network, attenuator, etc. Of that path. So each configuration, when I do that, we have to do a sanity check. So if I've got a low pass filter, when I'm checking the lower frequency range and I switch the rejection network to a band reject filter, I will need to recalibrate with that piece of hardware. So these can be quite cumbersome, and configuring these is a little bit intense. So be aware that there's a lot to do when the transmit verification system is in place for CE106. We determine the voltage limit -6 like normal and apply the signal generator and to midpoint of each one of the configurations. Execute the software, make sure it's all good, confirm it. And question comes up into this configuration: why is the dummy load necessary? Without having a dummy load, there's no current flow. And without current flow, the directional coupler doesn't perform as rated. I need to have a termination for the transmission in order to get the coupled signal over. So the dummy load replaces like a 50 ohm antenna, so we're creating an equivalent current and lets the directional coupler work as it should. let's move over to the RE101. I'm going to go ahead and go through the emissions things before going into susceptibility. The RE101 verification checks the hardware, and you configure it as part A of the diagram with the signal generator replacing the antenna. So suddenly our antenna is not there. And so we need to be aware of that. Now the measurement receiver thinks it's there. We told it we're doing an RE101 test and we're using X antenna. So the antenna factors would be applied. So now when I come up with my voltage to be applied, I need to also subtract the antenna factor minus 6 dB to arrive at a test level. And because the software thinks the antenna is there, so it's going to add that antenna correction factor, or conversion factor, and apply it, so we'll suddenly be way out of range if we didn't account for it on our injected signal. We adjust the generator to that level, execute the measurement to collect, and verify that it works okay. The part B, or the lower section of the diagram, simply puts a resistor between the center pin and the connector shell on the loop antenna to see that our resistance is the same as it was as built. Normally these run in the 5 to 10 ohm region, but I suggest that you do your antenna checks and record what you get early when you initially get it, and then see if it starts changing. The turns inside, or the wire turns inside the loop antenna could fray, or somebody decided to use it as an injection and overpowered it, producing some insulation breakdown. So the idea is we need to see that we're consistent with it. If we start seeing higher levels and they're consistently, a trend might indicate that we need to have the antenna repaired, looked at, etc., or just simply replaced. They're kind of difficult to repair. The RE102 verification is much the same as RE101, checking the cables, receivers, and the data collection. Plus, we use a stub radiator thing to get an indication that the antenna is there. When we inject the signal, the antenna is not present, so we replace that like we did with RE101. And so basically we need to determine what voltage to be applied to test limit minus 6 dB minus the antenna factor for that particular frequency. Adjust the generator to the right level, execute it, see that we get the right answers. And we're at the required tolerances met. Use the stub radiator, and the stub radiator is defined by the standard as a coaxial cable with the shield removed and terminated, so it acts like a radiating antenna. And it just allows the signal generator to produce a radiated signal, and we put our antenna back on the end of the cable and see that we receive a signal. They're not asking for a particular level to be brought into being, and I consider that to be a minor pitfall, that sometimes we need more validation that the signal is appropriate. So quite often I'll set up a particular physical stub radiator relationship to the antenna and see that we get the same answers given the input is the same. Now on the rod antenna, we do another thing because it has an active element thing in the base, the amplifier, preamp, and the filters. So we connect a signal generator at several frequencies for the rod antenna, a little bit more frequency checks than the others. And we generate a signal and remove the actual physical rod and inject it through a 10 picofarad capacitor to where the rod was normally be connected. We account for those losses. The 50 dB termination allows for a 6 dB correction, and the rod being missed is a typical 5 dB correction. So we look at an 11 dB offset when we generate the signals, and we see that they measure properly given the coaxial cable. The details are in the standard. Most frequently when this happens, something goes wrong here. Remember that antenna has got a high impedance input circuit, the rod terminates, and it's real sensitive to ESD. So make sure you use a lot of ESD precautions when you're taking the rod antenna away and putting it back in. Get yourself attached to the base of the antenna so you've discharged yourself before you touch that rod connector place. You'll destroy your FET transistors in the antenna. Well, let's swing over to some susceptibility calibrations. And these calibrations are more or less setting the forward power, even though some of the equipment is checked, because, in order to overcome losses, etc., we'll adjust our calibration levels. It establishes setting for the maximum power to be recorded, and it also verifies the linearity of the test equipment. The limit is based on a power dissipated by a half-ohm load, so that's the established de facto standard for doing the test. Configure it like we see in the diagram, where our signal generator to a power amplifier to the coupling transformer. Now, some people measure the output of the the power amplifier, and some people measure the output of the signal generator. I prefer the voltmeter at the power amplifier output because it allows me to move the gain of the amplifier and reestablish the maximum voltage here. If I put it at the signal generator, the gain of the power amplifier should not be adjusted between the calibration and doing the testing. So be kind of aware of where you're going. There's a lot of information on this particular calibration, etc. And there's an article online in a blog concerning that. There's a link at my website regarding CS101 calibration. Configure the shown in the diagram. Adjust the source to the required voltage measured across the resistor. We normally measure the voltage, so to get at the low frequencies, 80 watts of dissipated power, we're adjusting it for about 6.32 volts on the oscilloscope. And we record what the voltmeter settings were on the output to say that we need to apply at least that much. Record these things as the maximum drive level. Using the signal generator settings is an alternative method, but sometimes, depending on the amplifier performance and feedback from our primary circuit, we end up with different results when we encounter that. So it's kind of a touchy situation. Again, that article discusses it in detail. And you record all the settings across the frequency range, capturing as many values. Whenever I change my settings or the voltage varies, I need to record that frequency where that occurred. If everything stays even and flat, it's not so many readings here. You might set it up to where you get a reading at every step or some things here, but manually you can do this. This test gets automated quite often, and there are several issues when we automate, and especially when we try to translate it into testing of an AC powered device. The article delves into that somewhat also. The CS114 has a similar type maximum power to be applied for the pretest calibration. By the way, I forgot to mention on CS101 that during the calibration check, we make sure that the waveform is always a sine wave to validate that we're not overdriving our amplifier and distorting the signal. It gives us a range that the amplifier is well within its tolerance. Back to CS114 here. The pretest calibration gets this forward power setting and looks at the injection and monitoring probe situations here. We configure the shown in the A diagram and tune it through the frequency range, recording the power to be applied. The directional coupler output is our typical measurement point here where we inject. So we're injecting a signal into the injection probe. It goes through the current loop built by the coaxial load and the measurement receiver. We note also that there's a monitor probe here that just simply comes over to a coaxial load. That came into being with revision G to allow us to do a thorough calibration check of the monitor probe. Now, that assumes that this monitor probe we're using here gets its full check out, so when we use it for other systems, this thing is checked out. Now, quite often if you use one probe for CS114 and a different probe for measuring CS115 where that's not there, we've done no calibrations to the CS115 test. So the idea is it's there, but there's a pitfall if we don't validate the probes that we're using for other things that's no longer getting the periodic calibration or the higher level validation checks. So that's one of the pitfalls that we need to be concerned about. After we record all the levels for the various frequencies going through this system, we play back that data using configuration B. And I moved my measurement receiver over to that monitoring probe. I play back the recorded signals that I did for the version A setup, and I should measure the current that I used to create the maximum settings. I'm creating signals equal to that, so the measurement probe needs to validate that they are right. So CS114 is got a lot of little detail about it, and quite frankly, the test is probably one of the most error-prone things that we do. People forget that what we're trying to accomplish with CS114. CS115 is very similar to CS114, except I'm operating in the time domain using an oscilloscope and validating the current of this waveform. We set it up for the test level to produce the waveform, see that all of our equipment's working right, and we record the settings it took to produce the proper waveform. Those settings are used during the test, and the current is measured versus being adjusted to some particular level. Because if the circuit impedance is low, the current waveform will be higher than we did during calibration. Remember that these calibration circuits are a 100 ohm circuit because we have two 50 ohm terminators in series with the current loop, the coaxial load and the 50 ohm termination for the oscilloscope. So we need to make sure the equipment has the adequate frequency response. If you have unable to get the transition time to nanoseconds or less, you might be having a bandwidth problem with your current probe or your oscilloscope, depending on that. So you need to look at some high frequency components to do this test. CS116 is very similar to CS115, except we go into a dampened sine generator to produce the waveforms. Again, the calibration verifies the waveform parameters and establishes a maximum drive setting. Unlike CS115, the waveform peak current is there, but we do not necessarily allow higher levels to be applied because the circuit impedance is low during test. So this is used with the maximum. When we're doing this thing, we're verifying the frequency of the damped oscillatory and the dampening factor, or the Q. How quickly does it deteriorate? And it's supposed to be some value that's recorded in a book. I think it's 15 plus or minus 5. And that is done by a particular formula that's provided in the standard. So, and we record the signal generator settings, and these settings indicate the maximum power. Ensure that the equipment has the frequency response for the fast transitions associated with the higher frequencies that we're doing. Remember, CS116 calibrates at least 6 nominal frequencies plus known resonances if we can establish those. Most of the time we have little information, and 461 is more generic, so we don't know where the resonant frequency may appear in the real installation. CS117 also has a voltage or current verification associated with it to verify the waveform and the ability to determine the current or the voltage level. These test levels are prescribed for the particular test, with the voltage waveforms have an associated current limit, and the current waveforms have an associated voltage limit. So if I don't get to the test level, I can default to the limit level. The waveform verifications and settings use the configuration as shown here. We use an open loop configuration to validate the voltage waveform, in order to limit how much current is flowing, and use a shorted loop for the current waveform, so we can determine what's the worst case element there. During the test, the generator settings defer to the measured voltage or thing in the circuit. The verification process simply demonstrates the generator capability to produce a proper waveform. Now, in most of these waveform situations, when we actually apply it to the circuit, the waveforms lose all of their shape because of the parasitic elements associated with the live circuit and the cable. So the idea is these are very similar. We just use the ground plane as the return path for the current monitoring loop, and the open loop prevents us from doing that so we can measure the voltage. This same configuration is used during the test, except the loop goes away and the UT becomes into that shorter open loop to determine how it works. The CS118 verification process validates the waveform and the ability to determine the test level. You'll see that there's a couple of steps involved here where the tip voltage verification is done. That confirms the simulator voltage matches the settings. So if we adjust the ESD generator to 8 kV, that electrostatic voltmeter should read 8 kV within the tolerance band. So we do that using an air discharge tip to see that it's present. The discharge current waveforms is a test that's done to a target with a contact discharge test method. Verifies the waveform conforms to the established human body model. The CS118 human body model is based on having a body capacitance of 150 picofarad and resistance of 330 ohms. And so it creates the waveform as we saw there. There's particular current levels associated with the waveform discharge. As you can see, there's some dots on the little chart down there to say we measure the current at those particular spots to see that it's performing right. Now this is done into a very specific target shown on the diagram there, and that target is mounted near a shielded enclosure wall. RS101 field verification comes into being here because we're not able to measure the field during the testing. It's not present. So we need to verify that the normal radiating loop for the magnetic field is based on the applied current, and it generates the appropriate flux density. The relationship is validated. So we calculate the current necessary to produce the test level flux density, where flux density in an air media with the standard probe is 9.5 E7 picoteslas per ampere. We configure the diagram configure the equipment as shown in the diagram with the field monitoring loop and a current probe or a low-level series resistor, something to be able to monitor the applied current through the loop. And we adjust the signal generator to a kilohertz to do this calculation. We measure the field at the field monitoring loop to confirm the current to flux density relationship. So, and this relationship provides the applied current throughout the frequency range. So basically, I'm going to calculate what the current should be to produce the flux density. I'll adjust the signal generator until that current is flowing, and then I'll connect my measurement receiver to the field monitoring loop to see that it gets the right answer. These field monitoring loop and radiating loops are a fixed design, and they follow through. I have a diagram of how they're built, but that's the standard configuration. So when you're doing this validation, we're just seeing that the current and net match at 1 kilohertz, that's the field and the current match, and it indicates the relationship is in fact valid. And we use that relationship to calculate what current should be applied during the test at all the frequencies. We generate that table and have the signal generator be driven until we attain that current output. Great, easy test to do automation tools with. They're out there everywhere. But the validation is something we need to take serious consideration about. I've kind of went through these things kind of hurriedly because my time has been fairly limited. So I wanted to get through several of them, but we're not going to get all of them because we normally use active measurements, or it's rarely accomplished test that not everybody's doing. For example, RS-103 could use a pretest calibration, but a lot of people use active measurements of the field as more common. The waveform verifications may not resemble the applied waveforms because of circuit characteristics. When we're doing the test, the waveforms take on a whole new pattern. In many cases, the verification has been expanded to verify the passive devices exempted from periodic calibration. And we discussed a few of those as we went through. Although the verification process applies to the test configuration each time that it's established, the record keeping helps us track individual items to identify when it was checked last. It's tough to go through searching for a series of test reports to find out if that particular asset number, ID number, serial number was used and when it got checked and how was the checks. So we need to do this thing. MIL-STD-461 constantly reminds us to use the equipment that we checked. I guess users may have created this reminder need because they would check some equipment and use something different during the test. Verification is a necessary function, but note some pitfalls do exist. Look those things up. Like I said, there's some articles available, and you need to establish some lab procedures if there are gaps in our process. I need to kind of wrap this thing up to allow a little bit of time for questions. So with that, I'll tell you how I can be contacted here at my Compliance Direction website. Reach out to me if you have particular questions regarding this, or if you need to see MIL-STD-461, more in-depth training and things of that nature. With that, I'm going to turn it over to the host for any questions that may have came in.
Thanks, Steve. That was a great presentation. I'm just going to hop right into the Q&A. First question is, in regards to the cable pinch problem, how many test frequencies should be checked to verify the cable is okay? If the pinch point has very narrow frequency response, it seems like a network analyzer may be needed.
I agree. In the article regarding this, where I got more detail, I did recommend a network analyzer to sweep the cable. It is a good checkpoint, and cables take a beating in the lab, so I don't downplay the fact that cables affect a lot of things. A sweep of the cables should be something to consider on a frequent basis.
Okay, and because of the response here, this is going to be our last question. But all questions that were asked will be answered and posted to our website. Here's the next question, Steve. CS114 calculation. I heard that the emission probe is also placed into the calibration setup since high gain probes can be an impedance to the induced current loop and might affect the resulting injection levels. Adding the probe provides the same impedance in the loops as would be found during actual testing, especially since the impedance is between the injection probe and the EUT. Is that correct?
Well, I agree that the injection probe places an impedance and can affect the impedance of the cable, but I don't know that it transfers over from the calibration to the test configuration, because the cable impedance becomes a lot of a variability based on how it's placed, how far above the ground plane, how close are the cables. So I don't know that we're seeing a huge influence in the test arena. I know it does check the calibration of the probe, but how much effect it has on the impedance when we move from calibration over to current, over to the test, I've not really explored it very much. It's a good question. I'll need to look into that a little bit more.
Excellent. So, Steve, I want to thank you once again for your presentation. I also want to thank everybody who attended this session and asked questions. I thought it was a very engaged group. I also want to thank our sponsors, AR, for sponsoring this session, but also the entire event. Few housekeeping notes: you will be receiving a URL for an on-demand version of this presentation. And as I previously stated, all questions that were asked will be answered and then posted to our website. Once again, thanks for attending, and I hope everyone has a good day. Thank you.